So we are going to talk about computer haptics today, and I will give you an introduction of what haptics means.
Okay, so I'm thinking of things like force feedback on a controller on a computer, video game or something. Is this the sort of thing we're talking about?
Yes, it is one aspect of haptics. So when you think about mobile phones or game controllers, there are typically vibrations, and these are about your tactile sensation or cutaneous sensations that are about fingertip receptors or stretches.
So when you type on an Android phone, it makes
it makes little buzzes, and when it rings, it buzzes as well. This is one aspect of haptic feedback, and the other aspect is kinesthetic feedback or proprioceptive feedback, which talks to our senses of forces, position. So it is how haptic feedback is transferred through our joints and muscles.
So this must be the sort of hard stuff to get right. Like when you shake someone's hand, you sort of feel how hard they're shaking and you shake back. But a robot, how does that do that? Is this the sort of thing we're going for?
It is similar, but when you think about touching a human, it is actually very much complex. So the thing about haptics is really distributed. So we get information from multiple channels because there are a lot of different sensors on our body, especially in our hands, and we combine them. So it's a combination of forces, for example, how much you're squeezing, which is about pressure, and then how much you're moving, for example, which is about the forces that you're applying to. And robots today, they are only capable of realizing some of it because we don't have sensory technologies that could sensory and actuation technologies that could make it very comparable to human haptics. When I talk about computer haptics, this is a little bit different than how you would realize the sense of touch with a robot. It is about how you can create a virtual world, like a simulation, a computer graphics game, for example, and you implement a device to feedback forces to you. So when I talk about haptics today, what I refer to will be kinesthetic feedback, force feedback, and what we are going to talk about is how these forces are computed when you see a scene. And the scene would be a simulation, but it can reflect to the real world as well. And within this simulation, we assume that there are objects that we want to touch. So this is, if you can see, a haptic interface, and it moves in the 3D space. So this is a grounded haptic interface which has actuators, and what it reads is the position and the orientation, although it doesn't really drive torques at your hand, it only gives you force feedback. This is an impedance type device, which means that it reads positions and gives you forces. There are other kinds of devices as well, but this is the probably most common of haptic force feedback interfaces that you can have. We also have different interfaces which you can, for example, wear, like exoskeletons or force gloves, and they do operate on similar mechanisms as well. So we are going to talk about how we actually use this almost as a mouse and then go and touch an object on a virtual space, on a 2D screen. So I can actually talk about this as a sensing actuation problem, where you sense the data, which is positions in this case, and you have then a simulation loop, which consists of a visual loop and a haptic loop, and then you have the actuation. The visual loop operates typically at a very low frame rate, like 30 Hertz, 60 Hertz. However, the haptic loop, in order to be stable, it needs to operate at a much higher rate, which is traditionally 1000 Hertz.
Oh, wow, okay.
So every millisecond, you have to make a computation and send it back to the device so that the device would give you something meaningful and stable. Let's say we have a haptic device here, which is similar to this, that can read data from encoders. So we have encoder data, which means I can read the state of the robot arm, which is typically the joint angles. And I know the model of the haptic device, so I can compute the position of the tooltip or the end effector or the interface point, as we call it. So the encoder data is fed into something that we call forward kinematics. And this is very traditional in robotics. So you can get the state, the joint angles of a robotic device, and because you know the model, you can compute where the tooltip is. And this is the easy problem. Then forward kinematics computes a position. That position is used to interface with a simulation. And within the simulation, I have objects. These objects can move. These objects can be static. What I need to do in order to enable haptic rendering is very similar to what we do in computer graphics, to look into collisions. So the position of the tooltip is taken, and that is checked for collisions with objects within the scene. So I will call this collision detection.
People will be thinking of, again, video games with this, won't they?
It is the same principle. So haptics and computer graphics, they are extremely similar. So many of the methodologies, especially in haptic rendering, is adopted, I think, from computer graphics. Some differences is in simulation, you want to show visually something that is compelling. The aim of haptic rendering, in contrast to visual rendering, is to make someone feel something real.
Physical, yeah.
Physical. And the one other difference is the frame rate. So this needs to be really very quick, whereas this tolerates failure a little bit more. Tactile sensations or haptic sensations are much faster. We wouldn't really see if some frames are dropped or if they are injected with some information. We would feel better discontinuities, and they are what we put meaning into when understanding the world, explore the world. But also from a robotics point of view, the discontinuities make the robot unstable, so the behavior is not realistic. So collision detection takes some information from simulation, which is where the objects are, for example, the tetrahedral or triangular models that are comprising the simulation elements. We have the position of the device, the tooltip, and we compute a contact point. Once we have the contact point, we need to compute a collision response. So in graphics, a collision response could be you push one object and it moves and it touches something, so there is a cause and effect. So you issue a force, and there is a physics model behind the simulation which makes things happen. And this is the same principle. You touch something and you generate a force. The object can move in response. The collision response would compute a force vector, to be felt at the tooltip or in my hand if I was pushing it, if the system was completely transparent. And then that force is sent to the simulation and to the haptic device. The force that you send to objects in the simulation and the force that you should send to the device may differ. So you could have some force modulation here, which could be scaling or putting it into the ranges so that you don't harm the device, or
right.
It could be...
So it's a bit like, again, like graphics, you scale to what the monitor is capable of displaying rather than, I don't know, burning it out.
Yes, exactly. It is very similar. So you move your mouse, for example, 5 pixels, but then your agent moves 5 meters.
Right.
So there's a scaling over there. So I will draw 2 arrows here. One is the force sent to the simulator if anything is moving, and the other one would be the force that you should feel at the tooltip. When it comes to the device, what I can control is the torques that I send to the motors. So there is another block here we call the inverse kinematics. And this is the harder problem when you compare it with the forward kinematics, because it solves the inverse problem of what should be the state of this robot. It's not a hard problem, as it is MP hard or anything, but it is less straightforward than forward kinematics, and we do have very established methods for the inverse kinematics as well. And this computes torques. As I said, this kind of operates at 30 hertz, let's say, and this has to operate at at least 1000
Oh,
hertz.
so it can be more than that then?
It can be more than that. But if you drop down, then you would start feeling it's not really stable. And in force feedback robotics as well, that becomes a bottleneck, especially if you're dealing with, for example, plate systems, if you're sending a robot arm to a space station and you're doing a delayed teleoperation and so on. So this is our bottleneck.
Okay.
Okay, so this is exactly what we are doing, and I will now talk a little bit about how we do the collision detection and how we do the collision response, so we could feel some objects in a scene. So as you may know, if you're interested in computer graphics, objects are discretized. So you may have a polygonal object, which consists of triangles. And the most naive way could be, I have this point, this mouse cursor, and I have thousands of triangles. In order to check for a collision, I could just check with every triangle. But then this is very slow, especially if you have to do 1,000 operations in a second. This gets very slow. So what we do in Haptics is we use bounding boxes, and we use hierarchical bounding boxes, which is similar to this OC3 algorithms, where you have a bounding box for an object, and then you check whether there is a collision with that bigger bounding box. If not, you should feel nothing. With a haptic device. It should be really transparent, as if you're holding nothing in your hand. And if you have a collision, you start dividing it into smaller sections, so you don't actually search the whole space, but you only look into a small set of triangles. And why this works is also because of the observation that once you detect where you are, then the search space really becomes very, very small, because humans actually can't move that fast. Okay, so that makes the search problem very, very quick. And once we know we are reaching an object, we have a surface that we are testing against, the collision response, the computation of the collision response, the forces, is the problem. So I'll go over the simplest example here for a point-to-line, point-to-surface collision detection. You could know when you're not touching the object, and this is your haptic interface point, which I will write as hip. The force in this situation should be 0, because you're outside and you shouldn't really feel anything. The device should feel really empty, as if it's not existing, which we call transparency in robotics. And when you touch the object, in haptics we allow the hip to pierce into the object. In graphics, you would see something on the object, so visually you should see the object as here. But in order to compute forces, you need some kind of formulation that allows you to compute...
to see how much forces... Yeah, okay.
Yes, you should apply to pull you away from the object. So in practice, what you would do is you would allow the hip to pierce into the object, and then you would place a little virtual spring here. And then the force you compute would be simply the spring force. You would set a stiffness parameter K, and that would define your material properties. So I can show you a very simple demo. So what you see here is now I turned on this demo where you have 3 different surfaces. So one of the surfaces is characterized as being soft, the other one is medium, and the other one is hot. And so this is a representation of my cursor here, which is very similar to the end effector. And when it touches very slowly, you could see maybe something like a springy movement. Yeah, and if you look at the device, it's kind of really springy. You could see how the force is modeled. So it does act like a spring. If I go to a harder object, then you could feel it more. And the hardest object, then you would really feel that you're actually sliding on
So
the surface.
inside there, all the motors are basically saying, don't let that probe go any lower down, right?
Yes, they are saying that because I am very slow. So I'll also show you something different here. Because this is all about movement, right? I had a haptic interface point, and I'm moving it in space. So I'm really very slowly approaching this. So I'm not really piercing the object a lot, right? So you don't actually see that this is really getting into the, you could see the sphere pretty well. Maybe you see some kind of piercing motion that you see the bottom is getting in. But what happens when I become a little bit maybe faster? I'm not really holding it very much.
Bouncing.
So it's bouncing.
Yeah.
So I'm actually making it go into something unstable. And you can also see it's sometimes popping through.
Right.
So it's getting under the object where it shouldn't be allowed to. And why is this happening? Because it's just positions. The rendering algorithm doesn't know where I am. So what happened over there is I was moving the hip, and then I was moving it very fast. So I was actually going really like here. And then the force that you compute gets quite large, and it makes you pop out of the object, jump and bounce back. And then this can actually escalate as if, it can escalate really badly. In this case, it didn't, but it can also get very, very unstable, so you have to terminate the simulation. Another issue that happens is, for example, when we have a very thin object, which was also the case in this example, where you would compute forces that would push you away from the body of the object when you approach from this direction, and away from the body of the object if you approach from this direction. But if I'm coming, and if I'm really fast, I could actually pop through. Another thing that could be a problem is if I have a complex object, then I would represent it as a few subsections. And in this subsection, for example, if the hip is here, I would find the closest surface and compute a force that pushes me in that direction. So this is the forces that you should feel for this surface. And if I'm here, I should be actually feeling forces against this surface, so that my interaction would feel like I am on these points. But if I am approaching, and if I'm moving from here to here, then you would feel like somebody is popping me out from the side. So these are not realistic. This is not something that we would expect from a good force rendering implementation.
Would that be helped by making it faster?
It could be helped, but also it is about the characteristics of the device. Each device has a limit on how much stiffness that they can tolerate, and obviously about the frame rate as well, the server rate. So I can still pop through objects, and it is not very desirable. So how we eliminate these in haptic rendering is through proxy algorithms, where I actually have almost shown you the first idea that comes to mind. If I am rendering force, instead of computing just the distance about this piercing distance, I could compute an error, and I could try to minimize that, right? And the error would be the error between where I should be and where I am literally. So instead of actually trying to represent the distance to the line, I could define a proxy point, which would solve the issue of jumps, and I could compute a spring between the proxy and the object. So at any time, you could look into where the proxy is by looking into the collision detection, and you could compute a point where the proxy should be residing. and make the proxy walk over the object and make your hip only attracted to that, so that you would eliminate the
So
error.
it's trying to get back to where the proxy is at all times?
Yes.
Okay.
So this is sometimes called a God object algorithm, sometimes a proxy-based rendering. And it is a much better way to display forces. So that's all. And this proxy method is a method for haptic rendering, but they also are used for human-robot collaboration. So in our research, we typically use proxy points for human-human or human-robot collaboration, where you have a robot interacting through an interface point, a human interacting through another interface point, and they get connected through a proxy, which then connects to the task and operates it. And this way you could do a lot of intelligent things like assigning dominance behaviors to the human and the robot, separating their inputs from each other so you could analyze them better, so that the proxy becomes not a proxy for rendering only, but a proxy for agreement between the two actors.
This is like an ongoing open problem. It's not something that's considered solved, is it? Or is it just there are different ways of approaching it?
I think you could consider haptic rendering in some ways solved. So there are mechanisms that you could simply do things, but there are still issues, for example, when you represent material properties, such as what exactly I am feeling, because we didn't really talk a lot about friction or material properties that make this feeling realistic. What is it that I feel when I touch a sponge? Something like this, or something like a table. So there are libraries to enable this kind of learning of object properties. Also, transferring the haptics over distances and so on is I think still an open problem. So there are coding mechanisms, just as we do video coding or haptic coding, but it is still open. We can't really tolerate very delayed communication with haptics, so there's a lot of work going on in teleoperation architectures, but also packaging the haptic information and sending in distances. If the goal is to move from start to goal, and if I can't actually have an analytical solution, I'll do pink.